Okay, this is part one of a discussion of collisions. Broadly speaking, there's two kinds of collisions for us. One is inelastic, which I'm going to be talking about here, in which kinetic energy before and after the collision is not conserved. And the other one, which will be part two, is elastic collisions, in which case kinetic energy before and after is conserved. And so just conceptually, the difference is for an elastic collision, the bodies distort but then spring back to their original shape, and so the kinetic energy is temporarily stored in spring energy inside the bodies as they compress, but then it's released back into kinetic energy as they decompress. And that's why conceptually the kinetic energy before and after is conserved. For inelastic collisions, which is part one here, you get a permanent distortion of the bodies. And the result of that is, one result is that the kinetic energy after is less than the kinetic energy before. The missing kinetic energy goes into delta E thermal. Bodies are warmer. Okay, so the extreme version of an inelastic collision is where objects that are moving relative to each other before the collision hit each other, they collide, and then after the collision they stick together. That's called a perfectly inelastic collision. So as an example of that, let's consider a 200-gram glider and a 400-gram glider that are on an air track, so there's no friction, and they have initial velocities of 1 meter per second and 0.25 meters per second respectively. And let's say that they stick together. That would be a perfectly inelastic collision. So we'd like to do two things. We'd like to find the final velocity. Since they've stuck together, that will be the same for both of them. And then we'd also like to compute delta E thermal. So what we're going to do is we're going to take the system to be both gliders. So for the A calculation, we're going to set the initial momentum equal to the final momentum. This first term is the initial momentum of the 200-gram glider. The second term is the initial momentum of the 400-gram glider, and then we can set that equal to the momentum for both of them stuck together. You can see there's only one unknown in that equation, v sub f, so we can solve that and conclude that 0.17 meter per second is the final velocity of the two masses stuck together. In order to find out what delta E thermal is, we can calculate the initial kinetic energy. So this first term is the initial kinetic energy of the 200-gram glider, and the second term is the initial momentum of the 400-gram glider. That comes out to 0.1125 joules, and then we can then calculate the final kinetic energy of both of them stuck together. We've computed the final velocity using conservation of momentum, and so that's very easy to do. You can see we get a final kinetic energy which is quite a bit less than our initial kinetic energy. So the difference, Ki minus Kf, is 0.104 joules. That's the delta E thermal, and the implication of that is that the masses are warmer after the collision. Okay, let's do one more example here. If I can go to the next page. And so what we'd like to talk about is an inelastic collision called the ballistic pendulum. And so the scenario here is we'd like to measure the speed of a bullet coming in from the right, embedding itself into a wood block. And in this experiment now, there's two transitions that occur. So first of all, in transition number one, the bullet hits the block, and the bullet plus the block undergo an inelastic collision, giving the bullet plus the block some initial velocity v1 to the right. In that transition, momentum is conserved because it's an inelastic collision, but the mechanical energy is not conserved because delta E thermal is bigger than 0. Then in the second transition, the bullet plus block then swings up to some maximum theta, and at the maximum theta, that's a turning point for the motion, and so that would mean that the final kinetic energy is 0. Then mechanical energy is conserved during this second transition. And recall that we do have an external force, tension, acting on the combined mass of the bullet and the block, but since the tension is perpendicular to the displacement, W external is equal to 0, and so therefore mechanical energy is conserved in the second transition. And so we have some particular numbers here. We have a 10-gram bullet and a 1,200-gram wood block hanging from 150 centimeter long string. And the bullet then embeds itself in the block. The block swings to an angle of 40 degrees with respect to the vertical. So what we'd like to do is to find the bullet speed and then find delta E thermal. So let's pursue that. Alright, so transition 1, we're going to have conservation of energy, which means the momentum of the bullet before the collision with the block is equal to the momentum after the bullet with the block. Now, we do not know what V1 is at this point, but transition 2 will allow us to determine V1. So for transition 2, we're going to take the system to be the bullet, the block, and the earth. I want to now bookkeep gravitational potential energy, so the earth needs to be in there. The mechanical energy is conserved during transition 2, as I've said, but momentum is not conserved. And then the footnote there is that the work done by the tension is 0, and so W external is 0. So what I want to do for conservation of mechanical energy in transition 2 is to note that the initial kinetic energy is equal to the final gravitational potential energy. And so when 1/2 little m plus big M times V1 squared is equal to little m plus big M times G times delta Y, where delta Y represents the upward displacement of the bullet and block to its maximum height above its starting height. And delta Y is equal to L minus cosine theta. This is a calculation we've done in class. So now we can put this together to calculate V1. V1 is equal to the square root of 2g delta Y. Delta Y is equal to L times 1 minus cosine theta. And so I can put the numbers together here and conclude that V1 is 2.62 meters per second. This is the rightward velocity of the bullet and block immediately after the bullet has embedded itself in the block. But if I know V1, then now I can calculate V naught x, which is the initial rightward speed of the bullet. And the result of that calculation is a large number multiplied by V1. This V naught x is large because you have a small mass dividing a larger mass, considerably larger mass, and so the result of that is 317 meters per second. Just for kind of a reference point here, the speed of sound is about 340 meters per second. So this is a subsonic bullet, but it's moving right along. Kinetic energy calculation will give us what the delta E thermal is, and so I can easily calculate the initial kinetic energy of just the bullet, 503 joules, and then the final kinetic energy immediately after the collision is V1 squared times 1/2 times the combined mass of the bullet plus the wood block, 1.210 kilograms, 4.2 joules. So look at this, 503 joules before, 4.2 joules afterwards. That means delta K is Kf minus Ki minus 499 joules. Most of the energy is going into delta E thermal. So you have a pretty hot bullet, um, probably um, with a charred hole inside the wood block.